Hey, g'day, it's Prezzo. Thanks for stopping by. I'm working on the Stuart Turner 10H steam engine again today, and we're going to make the last of the major parts for the engine. That's going to be the eccentric and the eccentric rod and the strap. Right, I'm on the bench over here and I want to show you what I have in mind for those parts. We're not strictly following the drawing for these, but it's going to be, I think, a better solution to the whole issue of driving the slide valve inside the engine. So let's have a look. These are the parts that are supplied in the kit for the valve gear. So this piece of stock here is for the eccentric. This one piece pressing or stamping is for the eccentric strap and the rod in one piece. And this is the slide valve. Now we'll be using the slide valve, nothing wrong with that, it'll work perfectly in this application, but I'm not happy about using this part here. Now my reasoning for that is that in full-size practice this part would never be made of either brass or bronze. It would be made from forged iron or forged steel, sometimes fabricated from several pieces of steel stock, as you can see in this diagram here, but certainly not this material. Now you might be thinking, well, why not? What's wrong with it? And the answer to that is that this part is actually very highly stressed in the operation of the engine. And reasonably you'd say, well, why would it be highly stressed? All it has to do is slide this little valve backwards and forwards during the rotation of the engine. Now it turns out that there's more to it than that. If you take a slide valve like this from a full-sized engine, and let's just say for argument's sake it was 8 inches square. Now that means you have a total area of the surface that rubs up against the port face on the engine of 64 square inches. Now if the engine was operating at a steam pressure of 140 pounds per square inch, that means you have a total value of 8,960 pounds of force acting against the surface of that slide valve. And that's a lot. And if you take a factor of 0.02 as the force required to overcome the friction from that amount of pressure, you end up with 179 pounds required to move that slide valve backwards and forwards. Now in reality it's not exactly that amount for the whole cycle of the engine, it varies. But at some points it would be 179 pounds of force required to move that. That's equivalent to 80 kilograms or 81 kilograms, which is about my body weight. So yes, the force acting on this rod here is quite high. And over a period of time running at that pressure, that rod is likely to fatigue or to stretch or bend or buckle. So you want to use a material with a fairly high tensile strength. And I'm afraid this just doesn't cut it. So we're not going to use that. I'm not going to use this either. The reason for that is that the way I have designed the alternate to this part here requires a slightly larger diameter stock to make the eccentric. So let's have a look at the bits that I've got. So here is the redesigned parts for the engine. So this is just 3D printed in FDM plastic, but this part is the eccentric rod and it will be a separate part bolted to the eccentric strap with 2 ABA hex-headed bolts. The eccentric itself will be made of cast iron and it will be in 2 parts. So this top plate here is just a flanged plate to keep the eccentric inside the strap so it can be removed. And the other half of the eccentric has a flange on the bottom side. So when the assembly is complete, these plates or flanges will keep the eccentric inside the eccentric strap. Now instead of having a large boss on one side of the eccentric which will have a set screw fitted to the crankshaft, I'm going to try to fit the set screw through the body of the eccentric so that you don't have any visible boss on the outside of the eccentric itself. Now, that makes assembly and setting the valve a little bit more difficult, but it's completely doable and I think it's a neater look. In full-size engines the eccentric was sometimes held onto the crankshaft with a key and also a separate set screw, as you can see in this diagram here. So it's similar to full-size practice in a way. Now one of the reasons why I'm making this redesign is that I want to fit a white metal lining on the inside of the eccentric strap. Now this is white metal or babbit as it's sometimes known. And we're going to melt that and fit it on the inside of this part here. And my reason for doing that is that I'm not making these parts from steel or iron. They're actually going to be made from stainless steel. And you're probably thinking, Mark's lost his mind. Why is he trying to make these little tiny parts out of stainless steel? Well, I'll show you. Now these are the parts that I'll be using. These are made of 316L stainless steel, and yes, they are 3D printed, and no, I did not print them myself. Now the background to this is that I was contacted by a company a while ago called JLC PCB, and they asked if I would do a collaboration with them. Now I politely declined, and my reasoning for that is that I don't think you want to sit there and watch an ad that I have made for a large corporation. And also I'm not comfortable with the idea of somebody offering me free stuff in return for favourable comment about their product or their service. But then afterwards I got curious and I had a look at their website and found out that they do actually 3D print in metal. Now they do other 3D printing as well, and the part of the business that does that is called JLC 3DP, and they can print in SLS or SLA. Now I think this is called SLM, which is selective laser melting, and the only metal they offered was 316L stainless. And I was curious, so I went ahead and, without telling them who I was or asking for any sort of kickbacks or favours, I just simply ordered the parts and paid for them. Now the cost of these parts, I think this part here was about $8, this part was about $12, that's US dollars. By the time you convert that to Australian pesos and include shipping, I think I paid about $40. Now, I think that's good value, and these parts are actually amazingly crisp and accurate. Now I've run calipers over these, and they are within microns of the sizes that I modelled the original STL file. And that's all you need to do, is you just model the part, upload the STL, they will quote on the part, and also they will give you a report telling you if there's any issues. And originally I wanted to be able to print in the holes, the fixing holes, which you can see there, and I also wanted to be able to print in a pocket for the oil reservoir. So you can see that little pocket in there, and that actually has a hole that goes right through the inside ball. Now when they sent me the report, they said that there were some very thin walls in some of those areas and there was a danger that the print would fail. And they said, do you want to take the risk? I said, no, I'll delete those particular features and just go ahead and print it. But I will be doing some other machining operations on this. So there you go, that's 3D printing of metal, and I think it's good value for money given that these parts are difficult to machine in that material. Could be done, but I was just, like I say, curious to see how it would turn out. Now, in fact, I went back later and I ordered some other parts for a different project that you'll get to see going forward. And so far, totally happy with this. I'm just curious to see how it machines when we machine out this bore here and we drill the little holes in it. But we're not going to make that part just yet. We're going to go ahead and make the eccentric. We're using this material here, it's just cast iron. So we'll go over to the lathe and make the eccentric, and then we'll get stuck into this part here. Well, that's the bearing surface of the eccentric complete. What I'll do later on is part that off, leaving a very thin flange on one side, and then I'll part off a separate disc, which will be the cover plate to go on this side here. But before I do that, I'm going to drill for the two fixing holes to keep the cover plate in place, and then we need to offset drill and bore for the mounting that goes on the crankshaft. I put that cast iron stock in a square collet block in the vise on the Bridgeport, and initially I dialed in the center of that part with the spindle using my little touch probe here, and then I followed up with Stefan Gottswinter's compact ETI holder and ran that around the part, and I was within say 20 or 30 microns in one axis, and I've just corrected that, so now we're directly over the center of that stock. And using touch DRO, I've dialed in the position of the 3 holes I need to drill in that stock. You can see here I'm currently set up over XY00. If we have a look at the workspace and we zoom in, here are the 3 hole positions we need to drill. So this hole here will be for the bore that fits over the crankshaft, and these 2 holes here will be drilled and tapped for 8BA. Okay, that takes care of all the hole drilling. I'll just tap these 2 holes now for 8BA. Then we can part off a slice that will be the eccentric and one of the flanges, and then another slice that will be the plate that fits on top. Okay, we're back on the lathe. I'll part off the eccentric plus the flange on this side here, but I'll break the edge with the chamfer bit first. And then we'll part off the second slice. Well, there's the 2 halves of the eccentric now. That'll be held together with 2 8BA hex-headed bolts. These outer faces will need cleaning up to get rid of that burr there. That's easy enough to do. I cleaned off the 2 faces of the eccentric parts there, and I've bolted that together now with 2 little 8BA hex-headed bolts. And you can see that the eccentric strap is going to be running between those 2 plates there. And there will be a single socket-headed grub screw fitted through the outside of the eccentric later on, and that will allow you to clamp the eccentric onto the crankshaft. We'll be able to get at that socket-head grub screw through a hole in the bottom of the eccentric strap just underneath the oil reservoir. But what we need to do now is get on and bore out the inside of the eccentric to take the white metal lining. I've got the parts sitting in the mill vise here on 2 thin parallels, and I've got some aluminium MIG wire on the moving jaw there. And I've clamped it up as tight as I dare to clamp it. I don't know how strong this material is, and I'm worried I might crush it if I go too far. We're only going to take light cuts here with a boring head, and I've run my little DTI around there, and I think I'm within about 0.08 of a millimetre. And I don't know whether the part is sort of crushed and is elliptical, or whether it's just not that accurate from the 3D printing process, but that's close enough. What we need to do is just bore out some clearance for the babbit or the white metal. So even if it's not perfectly centered, it doesn't matter. And when I finish pouring the babbit, we'll put it back in the vise using the vise stop here, and we can fixture it in the same position and then bore out the white metal. Seems to be going okay, but I'm taking very light cuts, 0.2 of a millimetre on the diameter per pass, and I've got 0.8 of a millimetre to go. So yeah, I think when you don't know the material, it's better to go slowly. I'm a complete chicken. Well, that was the last pass I was willing to take there. I pulled up a little bit short. I'm worried about how much strength is left in this part and whether it's going to crush from the pressure of the vise. But I'll get this out now and get it deburred and cleaned up, and then I'll show you the fixture we're going to use to pour the white metal. I'll get those burrs off. Well, there's a bore on that part finished now. I got rid of the burr on both sides, and if I place that over the eccentric, you can see the difference in size there. Now that will be the thickness of the white metal shell when we're finished. Now I'm actually going to pour it using this little fixture here. So that peg in the center is made of aluminium. In fact, the whole fixture is aluminium, and that means that the babbit shouldn't try to alloy or tin that aluminium fixture. So it'll actually release when we are done. We want to take it off. Now there's also a 5-degree taper on that little peg there, and what we're going to do is place that over the peg, and I'll use this little clamp to make sure that everything's held down firmly and it doesn't try to leak out the bottom. Now I was just doing some reading on this. You need to be sure that the part that you're tinning, in fact filling with the white metal, is absolutely clean. So I'll run this through the ultrasonic cleaner. It needs to be etched in hydrochloric acid, and you need to use a hydrochloric acid flux when you pour the white metal in there. And I'll heat the entire assembly to make sure that the white metal stays liquid long enough to thoroughly tin the inside of that stainless steel part. So tinning basically means forming an alloy with it, and that makes sure that it's absolutely bonded. Two surfaces are actually bonded together. So I'll get this cleaned up and then we'll have a go. Pretty much all set up to do this process now for pouring the white metal into the eccentric. So we're going to clean that part in this simple green solution here in the ultrasonic cleaner, and then we're going to get on and we're going to etch it in hydrochloric acid, and from there, without sort of handling it, we're going to try and get it into the mold and clamp it all down, and then we're going to heat the babbit using this sort of a ladle and a gas torch, and then we're just going to pour it in, but I'll heat this assembly up after we poured the babbit in there just to make sure that it all wets the inside of the eccentric. So let's go ahead and get this cleaned up. So let's give that 10 minutes and then we'll put it into the hydrochloric. Okay, we're going to rinse that, and then it's going into the hydrochloric acid etch. Alright, so this is the etch. It's been about 2 minutes. I can see some very fine bubbles coming off that part now, so it is reacting with the acid. We'll give it about 10 minutes and I'll rinse it again, and then I'm going to dry the part before it goes into the mould. I'm going to try and rub some graphite around the edge of the bore to try and contain the white metal and stop it spreading over the top surface. Okay, I just rinsed that in clean water, so I'm just going to dry that off. Now, I'm just going to run my graphite around that edge there. The thing about graphite is it sort of repels a lot of alloys. So silver solder, soft solder, babbit, this will help prevent it running over that top surface there. Okay, so we'll try and get it in our mould. And we just want to try and roughly center that. Okay, so there's the assembly now. You see it's nice and tight against the bottom of the fixture there. So I'm going to heat up the babbit, and then I'll put some zinc chloride around the inside of the part there. Oh, and I forgot. Totally forgot. I've got to block up that little gap there. Oh, you idiot, Mark. Anyway, I'll get that done, and then we'll pour the babbit. Alright, crisis averted, I hope. I've just jammed a very thin piece of wood in there. When that's wet with the flux, it should withstand the flame long enough. If it doesn't, we're going to have a mess. Okay, I'll reheat that in a minute. I'm just going to get some flux on the inside of this part here. Alright, so we'll top up the heat on our babbit. Okay. Okay, I know that looks a mess, but I think it's wetted around the inside of the part. Part of the problem here is that the mould wasn't preheated. So room temperature, you pour the babbit in, it freezes immediately, and then you've got to add residual heat to that to get it to flow. And although it's left a big round meniscus on top there, I think by the time we grind that off or file that off, it should be fine underneath. But it doesn't work out, can always do it again. Well, the good news is a little bit of wood in there has survived the heat treatment, and I've just added a bit more flux to the top of that to try and get it to wet out the very top edge. Alright, let's see how we went. Alright, there it is. Actually released a lot easier than what I thought it would. What I need to do now is get both of the faces cleaned up. I'll just rub that on a file, and then we can rebore the interior to the correct size to fit the eccentric. But yeah, I think it's turned out pretty good. Right, cleaned that up, first of all on a file and then on some emery cloth, and this is the surface that was on top where I poured the babbit in, and it looks great. It's filled all the way to the very edge of the stainless steel part, but underneath where it was against the fixture it's left a sort of a rounded edge, but I think it's going to be okay. The flange on the eccentric will cover that so you won't see it. And I'm going to put this back in the mill vise now and bore it out, but I'll use a high-speed steel tool. I'm not sure if carbide works well on this sort of soft metal. I'm a little bit nervous about using this boring tool. I've never used it before, and I had to make an adapter sleeve to go into the boring head, but we'll just take light cuts, see how it goes. 'Well, it seems to be cleaning up okay, but I'll bring you back when we're really close. Getting really close now. I'm actually at 15.51 and we've got to go to 15.89. So I'm just going to take one more cut and then we'll do a couple of spring passes and measure. And I want to try to finish with about 1/100 of a millimetre clearance. If we overshoot, you can close up the gap in the eccentric strap and get some adjustment that way, but I'd rather not rely on doing that. Uh, 15.75, yeah, really close. Alright, I'm just going to do a spring pass, we'll call it quits. I got a feeling I overcooked that. Oh, that's alright. Okay, I'll take that out and deburr it and we'll see how it really fits. Check out the burr on the back. I gave that a clean up on both sides and I can tell you now the eccentric is a really nice fit on the inside of that strap there. Now the other side is not quite as pretty. There's some texture there from the 3D printing process, but I think that's okay. And what I need to do now is to get a junior hacksaw and just continue that slit all the way through the white metal lining. That will give us that adjustment. Got a few holes to drill and then we're getting close. Next steps with these parts is just a lot of drilling and tapping and counter boring and so on. So I won't do any commentary, I'll just give you a sort of broad overview of what's involved and then we'll assemble the valve gear and see how it turns out. Alright, just because I know this is going to come up in the comments, I thought I'd address it now. And the thing is that I made this little arbor, it's like a little stub arbor for a small drill chuck. And it was great. You can put it in a collet, doesn't take up a lot of room, very quick to mount and so on. But some people had commented that the drill chuck had a fair degree of run out. Now I'd said at the time, no it hasn't, it's just a camera artifact, it's fine. And then I was reviewing the footage that I had shot with this chuck using the same arbor and realised that it did have a lot of run out. Now you don't notice it when you're drilling on the machine, but when I looked at the camera footage I could see that it had this significant amount of wobble to the drill bit. So I made a new one. So this one here was threaded into the back of the chuck. I gripped a dowel pin in a collet in the lathe, and then I centre drilled the back of the stub arbor, and then I machined down this section to 18mm to fit a bigger diameter collet. And I think now I've got it right. I've checked the run out, it's only about 0.02 of a millimetre, which is fine. So yeah, hopefully you'll notice that this one's a lot more accurate. The plan here was to drill a 1/16 diameter hole through into the bore of the eccentric strap to allow the oil to come from the little oil pocket to the bore. And although I got a hole started with a 1/16 high-speed steel end mill, it just wore the end straight off it. So this material work hardens very readily. I will have to order some carbide drill bits in order to get through. And the hole in the back of the strap, which allows the hex key to pass through, I think I'm just going to do that with a 2mm carbide end mill. That's the smallest I've got, and although it's a bit oversized, it'll still work. Oh, disaster. I've just worn the end straight off that carbide end mill, and I don't think I got right through into the bore of the eccentric. But just for now, I'm going to call it quits. I have ordered some carbide micro drills, and when they turn up, I'll see if I can continue that hole through into the bore there even if I have to use a couple of different sizes to get through. I can't really assemble the eccentric onto the shaft without that hole all the way through there. So yeah, bad words were said, but what can you do? It's surprising, yesterday I was able to drill right through that part of the eccentric there with a high-speed steel drill bit, but I don't want to risk putting a drill bit in the bottom of that hole there now. It'll be super hard, it'll just destroy the drill almost immediately. So I don't know what I'm doing wrong. I was using a continuous feed, like a constant feed, and I had cutting oil on the bottom of the hole, but yeah, what can you do? Alright, I'll get this assembled as much as I can. I'll show you where we're at. To finish up today, I've assembled the engine at this point. Now, none of the fasteners are done up tight, and the whole engine itself is quite stiff. And you typically get that with a new engine because each individual part has minor inaccuracies. All of those inaccuracies tend to cascade and make the whole engine quite tight. And that's typical. You need to then disassemble the engine, fit each individual part. That means make sure that the parts are polished, make sure there are no chips or burrs, reassemble the engine with lots of oil, and then you'll get it to run on air. So that's the plan going forward. The other thing is that I didn't anticipate that putting that 1/32 wide flange on the inside of the eccentric there would offset the eccentric strap by that same amount of 1/32. And that means that up here, where the rod goes into the yoke on the end of the valve spindle, it's offset by that same amount. And if I was to tighten up everything at this point, it would sort of jam. So what I will need to do is take 1/32 off the end of the main bearing to put everything back into alignment. But that's a fairly straightforward process. Now the good news is that I was able to bore through that hole that I made such a mess of with that 2mm carbide end mill, and I did that using these. Now these are carbide dental burrs. Now this one's brand new. This was given to me by a dental technician about 45 years ago. I've had them ever since and I've never used them for a project, but this was the time. So I put one of these in a Dremel and I just worked away at the bottom of that hole and eventually got this cutter to go right through. And these are shaped like a little dovetail cutter, but they're super sharp and it was just the right size for the job. So now I've got a neat through hole, and I can put that Allen key through that hole and find the grub screw in the eccentric, and then you can loosen it and tighten it. Now I still have to drill through the hole for the oil into the eccentric itself, and I went and ordered a set of those carbide micro drills. So I'm hoping that I can do the same trick there, just drill through with a Dremel and get a passageway from that oil cup through to the inside of the eccentric. So at least we salvaged that other hole without making further mess. Now I suppose you're wondering, am I happy with this 3D printed part? Well, it looks great. The finish on it, it sort of polishes up beautifully. It looks like steel and it looks correct for the engine. However, I have never worked with 316L stainless before, and I wasn't prepared for how easily it work hardens. So I destroyed a couple of drill bits, a couple of end mills, but we got there in the end. And if I was doing this again, I would probably try to model the parts very much closer to their correct size and shape, so it didn't require so much post-processing. And if I was to try and mill this out of solid stock, getting that oval profile on the rod would be really, really hard. You'd almost certainly have to do that with like a 4-axis machine, which I don't have, or you would have to do a lot of hand filing to get that. So just for the experience, I was happy to work with the part, but yeah, knowing what it's like now, I think I'd, yeah. Was it worth it? Yeah, it was worth it because it looks right. So yeah, I've got another project coming up with some 3D printed parts, and I'll show you that a bit further along. Not quite ready for it yet. Now, in the next episode, I will have finished off some of the minor parts, like the buckle for the slide valve. Slide valve's done. We'll get that assembled inside, make some steam fittings. I need to put the cleating on the cylinder. That's the decorative cover that goes over the outside of the cylinder. And I think then we're pretty much done. So there'll be 2 more episodes running the engine on air, and then I'll do all of the finishing work on it. That's cleaning it, powder coating it, putting it back together. So join me for that. That's going to be a lot of fun. So to finish up today, I've got some footage of some animals to show you. Some people had commented that I hadn't done that for a while, and the reason for that is that we've had like meters of rain, and when it rains that hard, the animals tend to just find shelter and you don't see them. But we've had some fine weather, so I got the camera out the other day and we've got some stuff to show you. And I've got some other interesting projects in the pipeline, so please join me for those. But for now, it's Prezzo signing out, and I'll catch you next time. Cheers. Right, don't chase it.